Some days vanish in a blink. Others feel like they're glued to the clock, each minute dragging its feet across the floor. You look up from a game, a conversation, or a project you love, and somehow 2 hours have disappeared. You sit in a waiting room or stare at a loading bar, and a single minute feels strangely heavy and long. The same clock, the same ticking seconds, completely different experiences. This is already a warning that time is not as simple as it looks on your wrist. Stay with us as we unpack that warning, and if you love slow, deep dives into mysteries like this, remember to like this video and subscribe so you can keep exploring time with us. Think about the last time you were completely absorbed in something. Maybe you were reading, gaming, painting, coding, or just talking with someone you care about. You slipped into that tunnel where the rest of the world faded away. When you finally surfaced and checked the time, you almost laughed. How did an entire afternoon evaporate like that? Your clock insists that 3 hours passed. Your memory insists that it felt like 20 minutes at most. Now flip it. Picture yourself standing in a long line, watching the person at the counter recheck some form for the 4th time, or sitting in a classroom or a meeting where you already know what is being said. The second hand crawls. Every glance at the clock is disappointing. It feels like you have been trapped there forever, but you check again and discover that only 5 minutes have passed. The same units, the same minutes, stretched and distorted by your own experience. From the outside, from a satellite or a physics lab, time looks neat. We define seconds. We build clocks that agree with one another with astonishing precision. We synchronize devices across continents. From the inside your head, time is a completely different creature. It speeds up and slows down. It thickens and thins. It leaves empty gaps and sudden jumps. It behaves less like a ruler and more like a story your brain is telling itself in real time. You can feel that in small, personal moments. The commute that disappears into a blur once you have driven it 100 times. The childhood summers that feel endless when you are living them, but compress into a handful of bright snapshots in your memory. The first time you do something terrifying, like public speaking or turbulence on a plane, when everything seems to move in slow motion. These are not tricks of language. They are clues that whatever time really is, your experience of it is not a simple readout. Psychologists have spent decades poking at this strange relationship. When people are bored or anxious, they tend to overestimate how long things take. When they are engaged and stimulated, they tend to underestimate it. In intense moments, like near accidents or close calls, people often report that time seemed to slow down, as if the world dropped into a different frame rate. But when researchers look closely, they do not find that the outside world actually ran slower. They find that the brain simply stored more detail. Later, when you remember it, more detail feels like more time. The unsettling part is that your sense of time is not a direct window to some external flow. It is a constructed feeling, built from many different signals. How much is happening, how emotional you are, how much energy your brain is spending, how much information it decides to save. Your inner timeline is stitched together from all of that. When life is quiet and repetitive, there are fewer stitches. When life is intense, there are many more, so your brain quietly stretches and compresses the same physical interval depending on what it is doing. This construction does not only affect your memory of the past, it also shapes the present you think you are living in. Your brain is constantly gathering signals from your eyes, ears, skin, and body, then lining them up and smoothing them out. Light from the world, sound in your ears, the position of your limbs, your heartbeat. All of that arrives at slightly different moments. The brain holds onto them for a brief instant, then assembles a coherent now. By the time you feel that now, it is already a tiny bit in the past. You are always living in a slightly delayed model. Once you see this, the old familiar picture of time as a universal river starts to crack. We like to imagine that there is a single flow, the same for everyone, that carries events from the future through the present and into the past. But at the human scale, what we actually live with is a patchwork of timelines. Your timeline, my timeline, the timelines of everyone around you, each one shaped and warped by perception, memory, attention, and emotion. The river is already broken into many streams before physics even enters the story. So we are left with an uncomfortable question. If our most immediate sense of time is so malleable, what exactly is out there? Is there a solid, objective time that exists independent of minds, ticking along whether or not anyone is watching? Or is time, at least in part, something our brains manufacture to make sense of change? The rest of this journey will trace that question outward, from psychology into clocks, from clocks into physics, and from physics into the deep structure of the universe. For now, hold on to this simple insight. The feeling of time that guides your days is not a raw fact of the world. It is a story your brain is telling, and stories can change. On the surface, it feels like you move through time the way a train moves along a track. First this moment, then the next one, then another, all lined up in a row. But once you peek inside the brain, that neat picture falls apart. Your brain does not sit there with a stopwatch, passively recording an external flow. It builds a sense of time from scratch, over and over, using shortcuts and guesses that usually work but sometimes go delightfully wrong. Those glitches are the cracks that let us see how the mechanism really works. Psychologists began by doing something very simple. They asked people to judge how long something lasted. A tone in headphones, a light on a screen, a boring task like staring at a dot, a fun task like a game or a puzzle. Again and again, the same pattern showed up. When people were bored or uncomfortable, they claimed the interval was longer. When they were engaged or entertained, they claimed the interval was shorter. Nothing in the outside world changed. The only thing that changed was the state of the brain looking at it. One way to picture this is to imagine that your brain has an internal metronome that ticks along in the background. One idea in psychology calls it a pacemaker. Each tick adds a bead to a mental string. When you look back and ask yourself how long something took, your brain counts the beads. More beads, more time. Fewer beads, less time. When you are anxious or highly alert, that pacemaker seems to speed up. When you are relaxed or disengaged, it slows down. The actual clock on the wall does not care about your mood. Your inner clock absolutely does. There is another twist. Your brain does not just rely on a steady ticking. It also pays attention to how much happens in that interval. Think about a walk you take every day on the same path. The first few times, your brain writes down a lot of detail. New sights, sounds, tiny surprises. Later, once the route is familiar, it writes down much less. When you look back on those walks, the early ones feel longer and fuller. The later ones compress into a blur. It is not that time itself has changed. The number of memories you laid down has changed, and memory is one of the main ingredients your brain uses to cook up a feeling of duration. Researchers test this with what they call oddball events. Picture a screen flashing the same simple image over and over. Your brain gets bored. Then suddenly a different image appears just once, for the same physical amount of time as the others. When people are asked which image lasted longer, they often pick the oddball. Their internal sense of time stretches around the surprising event. The brain carved out more attention and more detail for that one moment, so later it feels as if that moment owned more of the timeline. The slow motion effect during accidents pushes this even further. Many people who have been in car crashes or near falls say the same thing. The world suddenly seemed to drop into a different frame rate. Objects moved through syrup. They could notice tiny details like cracks in the dashboard or individual blades of grass. For a while, it was tempting to imagine that the brain literally sped up its processing, like a camera capturing more frames per second. But experiments suggest something subtler. During a terrifying event, your brain floods your memory systems with detail. Later, when you recall it, that dense, high-resolution memory feels like it must have taken longer. What stretched is not the physical event, but the story you built about it afterward. This reconstruction does not only happen for dramatic moments, it is baked into everyday life. You've probably noticed that days feel long while you are living through them, but months and years feel short when you look back. Childhood summers seemed endless at the time. In memory, they condense into a handful of scenes. As you age, many days look similar, and your brain compresses them even more. From the inside, the present can feel thick. From the outside, your remembered life can feel shockingly thin. That difference is another sign that your brain edits the movie of your past, rather than simply projecting a complete recording. Underneath all this are networks of neurons and chemicals doing very physical work. Systems that handle attention ramp up and down, deciding what matters and what can be ignored. Arousal systems change your overall alertness, which nudges your internal pacemaker faster or slower. Memory systems in the hippocampus decide which moments are worth filing away and how richly to encode them. Each of those systems has its own rhythm and delay. The feeling of time you get at the surface is the combined result of all of them, stitched into a continuous story. There is also the problem of the present. Your brain has to combine signals that do not arrive together. Light reaches your eyes quickly. Sound from the same event can arrive a fraction of a second later. Touch and signals from your body have their own delays. If you experienced each one separately, the world would feel out of sync, like a poorly dubbed movie. Instead, your brain waits for a brief window, then lines them up and presents them to you as a single moment. That means the now you feel is already a little bit in the past. The present is a carefully assembled guess. Some researchers think that what we call the present moment might span a small chunk of time, perhaps a few tenths of a second that the brain treats as one unit. Within that window, events can be shuffled and smoothed. This might explain some strange illusions where a later stimulus seems to change the way you experience an earlier one. It is as if the brain is not just reading from left to right along a film strip, but occasionally going back a few frames to touch up the edit before letting you see it. When you realize this, your personal timeline starts to look less like a fixed line and more like a constantly rewritten manuscript. Every time you remember an event, you do not just pull it off a shelf. You rebuild it using fragments, and in the process you can subtly change it. Your sense of how long it lasted, how it felt, and where it sits in your story can all shift. The same is true of the present. At any given instant, your brain is blending very recent past, incoming signals, and expectations about the near future into a single feeling of now. The dramatic conclusion of all of this is unsettling but also strangely freeing. The time you live in is not a direct feed from an external cosmic clock. It is an active construction, updated and revised by your brain every moment of your life. Your past is not a set of fixed, objective timestamps. It is a narrative your memory keeps polishing. Your present is not a razor-thin slice. It is a stitched-together patch of recent events. In the parts ahead, we will step outside the brain and look at how humanity tried to tame time with sundials and clocks, then how physics tore down the idea of a single, universal flow. For now, hold this thought. If your own mind can bend and stretch time so easily, perhaps the universe itself has an even stranger relationship with time than we first imagined. For most of human history, nobody carried time in their pocket. There were no buzzing alarms, no glowing digits on a bedside table, no calendar app whispering about meetings. Time lived out in the world. It was painted across the sky and woven into the turning of seasons. If you wanted to know where you were in the day, you looked up. If you wanted to know where you were in the year, you watched the path of the sun and the pattern of stars. Imagine an early farming village. There is no concept of 9:30 in the morning. People wake when the first light spills over the horizon. They work while the sun is high. They rest when it sinks. The year is marked by the return of certain birds, by the flooding of a river, by the day when a cluster of stars first appears before dawn. Time is not chopped into hours. It is attached to events. Plant when the rains come. Harvest when the wheat turns gold. Gather when the moon is full. Still, even in that world, patterns matter. If you can predict when the river will rise, you can plant more safely. If you can predict when winter will bite, you can store enough food. Ancient civilizations along big rivers watched the sky with almost obsessive care. In Egypt, priests noticed that the bright star Sirius rose just before sunrise, at roughly the same time each year as the Nile flood. In Mesopotamia, watchers of the sky mapped the wanderings of planets and the repeating loops of the moon. They began to see time as something you could read, not just feel. But reading time from the sky has limits. Clouds happen. Mountains block the horizon. If you're inside a temple or down in a mine, the sun is a rumor, not a clock. As societies grew more complex, people needed to meet, trade, pray, and work together on more precise schedules. It is one thing to say we meet when the sun is high. It is another to say the market opens at the 3rd hour of the day and closes at the 9th. That shift from soft event-based time to hard-scheduled time is one of the quiet revolutions in human history. The first tools for this job were simple, but clever. Sundials took the shadow cast by a stick or pillar and turned it into a moving pointer on a carved scale. As the sun crossed the sky, the shadow swept across lines marking the hours. The idea is charming. The sun itself writes the time on stone. Yet sundials fail the moment the sun disappears. They are useless at night, unreliable in bad weather, and awkward far from the latitude where they were designed. Nature gives you a free clock, but only on its own terms, so people invented clocks that leaned on other steady flows. Water clocks appeared in many cultures. You can picture a carefully shaped bowl with a small hole in the bottom, floating in a larger container. Water trickles in. When the bowl sinks, a certain amount of time has passed. Or you can imagine a jar that slowly empties through a narrow tube, with marks on the side to show how long it has been draining. There were also sand glasses, oil lamps that burned at a predictable rate, and candle clocks scored with marks so you could see how much of the hour had melted away. All of these devices trade one problem for another. Water flows faster or slower depending on temperature and pressure. Sand can clump. Candles burn at different rates depending on the wax and the breeze. Still, they were good enough for many purposes. If you wanted to limit how long someone could speak in a debate, how long a guard should watch the walls, or how long a monk should pray before handing the duty to the next. A slowly emptying vessel or a marked candle did the job. Time became something you could hold in your hand and parcel out. As religious communities grew more organized, the demand for regular timekeeping intensified. In medieval monasteries, daily life was structured around fixed hours of prayer. The community needed to wake in the dark, gather at set intervals, and maintain a shared schedule that did not depend entirely on who happened to be awake enough to watch the sky. Early mechanical bell-rung devices appeared, driven by falling weights and simple gears. They did not yet tell you the exact minute, but they could ring at fairly regular intervals, pulling an entire community into the same rhythm. Cities followed a similar path. Once you have markets, legal courts, guilds, and councils, you need ways to say not just tomorrow but tomorrow at a specific time. Public clocks began to appear in towers, often attached to churches or town halls. Many of them had only an hour hand. Minutes were still a luxury, yet their impact was huge. Now a stranger arriving in the city could look up and see the same time that everyone else was using. The sky was no longer the only authority. Human-built devices were starting to define the shared day. Behind all of this innovation sits a deep question. Why were humans so determined to chop the continuous flow of change into discrete pieces? Part of the answer is obvious. Coordinated work is easier when you can say we meet at the second hour rather than we meet when the sun looks like it is about this high. Trade, construction, irrigation, and religious rituals all benefit from a finer grid. But there is also a psychological shift. When you measure time, you start to feel accountable to it. You can waste it. You can be late. You can schedule it, sell it, or feel it slipping away. So by the time mechanical clocks with gears and escapements arrived, the world was ready. Time had already begun to move from the sky into human devices, from shared natural cycles into abstract hours and minutes. Your ancestors watched shadows crawl across stone, water drip through a hole, and candles burn down, and in each case they saw not just a process but a measure of their own lives. The more precise those measures became, the more tightly societies could coordinate, and the more time itself began to feel like a resource you could and must manage. In the next part, the simple story of sundials and dripping water will give way to the age of gears, pendulums, and ocean voyages. Clocks will stop being local curiosities and start becoming global instruments of power. And the question will quietly change from how do we follow time in the sky to how do we build a time so exact that entire empires can trust their fate to each tick. By the time gears enter our story, time is already starting to feel like a shared obligation. Bells call monks to prayer, markets to life, and workers to their posts. But early mechanical clocks are still rough instruments. They tick and tock with personality. Each one has its own quirks. Two clocks on the same street can drift apart by minutes over a single day. It is enough for a town, but not enough for what comes next. Because out beyond the horizon, on rough seas, timekeeping is no longer about convenience. It is about survival. Mechanical clocks grow out of a simple idea. Let a heavy weight fall, but control the fall with a series of gears and a regulating device. One early solution is the verge escapement. Imagine a toothed wheel trying to spin, and a small bar with pallets that alternately catch and release the teeth. Each swing of the bar lets the wheel move forward by one notch. Attach the bar to a foliot, a sort of horizontal balance arm, and you get a slow, regular tick. These clocks are not very accurate by modern standards. They can drift by an hour a day, yet they are steady enough to ring bells at roughly the right times, which is already a revolution compared to eyeballing the sun. Then comes the pendulum. When Christian Huygens designs the first pendulum clock in the 1700s, accuracy jumps. A swinging weight on a rod naturally keeps a regular beat, as long as the swings are small. With clever gearing, that steady swinging can regulate a clock that gains or loses only seconds per day instead of hours. Now, cities can ring bells far more precisely. Astronomers can time the crossing of stars across the meridian. Schedules tighten. The day becomes a finer grid. But on a ship rolling and pitching through waves, a pendulum is a disaster. The very motions the clock is supposed to help tame are the ones that ruin its rhythm. The heart of the navigation problem is this. Latitude, your north-south position, is relatively easy to find at sea. You can measure the height of the sun at noon, or the angle of a known star above the horizon. Longitude, your east-west position, is much harder. The Earth spins once in 24 hours. That means it turns 15 degrees of longitude for every hour. If you know the time at some reference point, and you know local noon on your ship, the difference between those times tells you how far east or west you have drifted. 1 hour of error means 15 degrees of error. Over an ocean, that can mean hundreds of kilometers. For generations, sailors rely on dead reckoning and rough estimates. They track their course and speed, guess at currents, and hope. Sometimes that is enough. Many times it is not. Shipwrecks pile up on hidden reefs. Fleets misjudge their approach to land. In one famous British disaster, a squadron returning from war runs aground in bad weather because the navigators are wrong about their longitude. Hundreds of lives are lost in a single night. Timekeeping has become a matter of national security. In response, the British government creates the Board of Longitude and offers a large reward to anyone who can provide a practical solution. Astronomers pursue the sky. They develop lunar distance methods that compare the position of the moon to bright stars, using tables to infer the time at a reference meridian. In theory, it works. In practice, it demands clear skies, stable platforms, and intense calculation. It is difficult on a rolling, wet, exhausted ship. Into this drama steps John Harrison. He is a carpenter by trade, not an academic scientist, but he is obsessed with the problem of building ever more accurate clocks. Harrison understands the weaknesses of pendulums and wooden gears on ships. He designs new escapements, uses special woods that naturally lubricate themselves, and invents methods to compensate for changes in temperature. His early marine clocks are large, intricate machines, more like pieces of furniture than pocket watches. They impress, but they are not yet the simple sea clock that sailors can trust in any weather. Harrison refuses to give up. Over decades, he builds a series of designs, each more compact and reliable. The one that finally changes the world looks more like an oversized watch than a chest. Inside is a balance mechanism that can keep time despite the rocking of the ship, shock-resistant components, and careful thermal compensation. The idea is straightforward in principle. You set the clock to the time at the reference port before you leave. You protect it from tampering. At sea, you find local noon by watching when the sun reaches its highest point. Then you compare local noon to the time on the clock. Every hour of difference is 15 degrees of longitude. Trials are dramatic. Harrison's sea clock is tested on long voyages, including to the Caribbean. While traditional navigation drifts, his clock remains astonishingly accurate. The ship arrives much closer to its intended landfall than usual. There are arguments and delays, but the essential point is settled. A well-built mechanical clock can carry time across oceans with enough precision to save ships and lives. Accurate timekeeping has become a tool of empire. Whoever can navigate safely can explore, trade, and project power across the globe. The impact ripples outward. Accurate clocks are no longer just civic ornaments or monastic tools. They are scientific instruments and strategic assets. They allow astronomers to measure the motions of moons and planets with new precision, feeding back into better maps and better predictions. They let surveyors fix long distances on land. They push craftsmen and physicists to chase down every tiny source of drift, from friction in the gears to the expansion of metal under heat. The demand for stable, portable time turns clockmaking into high technology. Yet even these marvels still rest on the behavior of carefully built machines. Metal springs, gears, and wheels oscillate and tick in complicated ways. They can be influenced by environment, by gravity, by wear. As good as they are, they invite a deeper question. Is there a more fundamental, more universal regularity that we can use to mark time? Something that does not depend on gravity or weather, or the skill of a single craftsman. In the next part, that search will leave the workshop behind and dive into the interior rhythms of atoms themselves. Time will shift from the swing of a pendulum or the twist of a balance wheel to the steady, invisible vibrations of matter, and our ability to measure the seconds of the universe will leap to a new level. By the 20th century, clocks had become astonishing pieces of craftsmanship. Pendulums swung with steady grace. Balance wheels ticked their way through storms and across oceans. Empires navigated with them, trains ran by them, factories organized their shifts around them. Yet even the best mechanical clocks had a problem. They were still machines made of metal and springs and gears. They wore down. They reacted to temperature and gravity. They could get better, but only up to a point. Physics itself was hinting that there might be a deeper rhythm to tap into. The idea that atoms might make good clocks sounds strange at first. An atom is tiny, invisible to the naked eye, a cloud of probability rather than a little billiard ball. But quantum theory tells us that atoms are also wonderfully regular. Electrons in an atom can only sit in certain energy levels. When they jump between those levels, they absorb or emit light at very specific frequencies. Those frequencies are the same every time for the same kind of atom, no matter where in the universe you find it. That regularity is exactly what a good clock needs. In the middle of the 20th century, physicists began to turn this into a practical tool. Imagine an atom as a microscopic tuning fork, vibrating at a specific, reliable rate. If you can build a device that listens to that vibration and keeps itself in step, then the atom becomes the master clock and your device becomes its follower. The wobbles of springs and pendulums no longer matter. What matters is the internal rhythm of matter itself. One of the key players in this story is cesium. A particular form of this element, often called cesium-133, has an energy jump in its electrons that corresponds to a microwave signal with a very stable frequency. Engineers build cavities where clouds of cesium atoms are exposed to carefully tuned microwaves. When the frequency is just right, the atoms flip between two energy states more readily. Electronics monitor that response and adjust the microwaves to stay locked onto the atoms. The result is a clock whose tick is defined by a fundamental process of nature. Eventually, scientists did something bold. They redefined the second itself in terms of that atomic rhythm. Instead of saying a second is a fraction of a day, tied to the rotation of the Earth, they said a second is the duration of a fixed number of cycles of radiation associated with that specific cesium transition. Earth can wobble and drift. Atoms do not care. From that point on, timekeeping was no longer anchored to the turning of our planet around its axis. It was anchored to quantum behavior inside tiny pieces of matter. The precision this unlocked is hard to grasp. A good atomic clock can keep time so well that it would drift by less than a second over millions of years. Engineers often describe their stability in ratios. They can be accurate to parts in a number with 14 or 15 zeros after it. At that level, details that once seemed irrelevant suddenly matter. The slight difference in gravity between the floor and the ceiling of a lab can cause measurable differences in the rate of time for two identical clocks placed at different heights. That is not science fiction. It is an everyday correction in modern timekeeping. These ultra-precise clocks live inside national time laboratories around the world. No single clock is perfect, so scientists compare many and average them to define what is called coordinated universal time, the global reference that sets your phone and computer. Signals from these clocks leap out through radio transmissions, fiber optic cables, and satellites. When your phone tells you it is noon, or when a financial transaction is stamped with a time, the trail leads back to cabinets full of equipment listening to the whispers of atoms. The reach of atomic time extends far beyond laboratory walls. The Global Positioning System, often shortened to GPS, is one of the most familiar examples. GPS satellites carry atomic clocks on board. Each satellite constantly broadcasts a signal that includes the time it was sent and the satellite's position. Your receiver picks up signals from several satellites at once. By comparing the arrival times and knowing the positions, it can work out where you are on Earth. This only works if the clocks on the satellites and the clock in your device are all synchronized to extraordinary precision. A tiny error in time translates into a large error in distance. Here is where reality begins to poke holes in our comfortable assumptions again. The satellites are moving quickly relative to the ground. They are also higher in Earth's gravitational field than you are. Both motion and gravity affect the rate at which time passes according to relativity, the theory Einstein will bring fully into our story soon. Engineers cannot ignore this. They build the satellites and their clocks with relativity in mind from the start. The clocks are set up so that once they are in orbit, ticking at their own slightly altered pace, they line up with the standard time on Earth. If they did not, the GPS system would drift and quietly fail. So now we're in a strange position. We can measure time with exquisite accuracy using atoms. We can coordinate entire technologies and economies around those measurements. We can even see tiny relativistic effects in our own backyard, like the fact that time runs a little faster at the top of a mountain than at sea level. We're clearly very good at building clocks, but the success of atomic timekeeping raises a deeper puzzle. What exactly are these clocks measuring? On one level, an atomic clock is counting cycles of radiation. Every tick is a certain number of oscillations of a quantum wave. On another level, it is marking out intervals in which processes can happen, during which planets move and hearts beat. The device provides a stable yardstick. Yet when we zoom out to the universe as a whole, we will find that this yardstick does not always fit as neatly as we expect. Different observers, moving in different ways or sitting in different gravitational fields, will still disagree about intervals, even if each of them carries a perfect atomic watch. The age of atomic clocks is the age in which humanity squeezed time into a level of precision that forces us to confront its weirdness. You can hold a phone in your hand that relies on quantum transitions and relativistic corrections to tell you where you are and what time it is. Your daily life rests on a network of devices measuring the seconds of the universe with astonishing care. In the next part, we will step back in history to meet the thinker whose ideas make sense of those satellite corrections and mountaintop experiments. We will enter the world of Newton, where time was once imagined as absolute, universal, and the same everywhere, and then watch how that picture began to crack. When you look at an atomic clock today, you're seeing a device that quietly assumes something very old and very deep. It treats time as a background stage. Seconds march forward one after another, steady and indifferent, while the clock simply counts them. That idea of a universal time, the same everywhere, flowing at a constant rate, reaches back to Isaac Newton and the world he helped create. For centuries, his picture of time and space framed not only physics, but the way people imagined fate, free will, and the future. Newton lived in a world already enchanted by mechanical clocks. Tower clocks rang out over cities. Pocket watches clicked in the pockets of merchants and nobles. The idea that the world itself might be a kind of giant mechanism was in the air. Newton gave that intuition a precise mathematical backbone. He wrote down laws that described how objects move when forces act on them. A ball, a planet, a falling apple, all obey the same rules. This was shocking in its simplicity. The heavens and the earth were no longer separate realms. They were parts of the same machine. In Newton's equations, time shows up as a uniform parameter. You can imagine a number line stretched from the distant past through the present into the distant future. Every event can be assigned a time on that line. The laws then say how positions and velocities change as you move along it. Time itself does not bend or twist. It does not depend on where you are or how you move. It is like a perfect invisible grid laid over reality, ticking away identically in every corner of the universe. To Newton, this was not just a convenient choice. He spoke of absolute, true, and mathematical time, which flows uniformly without relation to anything external. In other words, even if nothing happened, even if all clocks stopped and every mind went silent, time would still pass at the same rate. Human clocks are only rough attempts to keep up with this deeper hidden flow. That is a powerful and comforting thought. There is one cosmic schedule, one master timeline, and every event has its fixed address on it. Once you accept this, something else follows. If you know the positions and velocities of all particles at one instant of absolute time, and if you know the forces between them, then the future and the past are in principle fixed. You can evolve the system forward to see what will happen, or backward to see what did happen. This idea reached its most extreme form in a thought experiment often called Laplace's demon. Imagine an intelligence vast enough to know every detail of the universe at one moment, and powerful enough to perform all the calculations. For such a mind, nothing would be uncertain. The future would be as clear as the past. This deterministic vision is both thrilling and unsettling. On the thrilling side, it suggests that the universe is completely intelligible. There are no gaps, no special exemptions. The same laws that govern a falling stone also govern planets, comets, and tides. With the right mathematics, you can predict eclipses centuries in advance. You can design orbits for satellites. You can build machines that harness forces instead of merely enduring them. Newton's framework fueled an explosion of engineering and astronomy that reshaped the world. On the unsettling side, it seems to leave little room for genuine choice. If every action you take, every word you speak, is the inevitable result of conditions long before you were born, where does that leave free will? Philosophers wrestled with this for generations. Some argued that freedom is compatible with determinism, that what matters is whether your actions flow from your own character and desires, even if those have causes. Others argued that true freedom requires some break in the chain, some element that is not fixed by prior states. Underneath many of these debates lies Newton's smooth timeline, marching forward with silent certainty. There is another way this picture seeps into everyday thought. If time is absolute, then there is a single correct answer to questions like what time is it right now? In such a universe, you can imagine a cosmic clock showing the one true time. Any difference between two clocks is simply an error, something to be corrected. When people synchronized railway schedules, coordinated factories, or set up international standards, they were, in a sense, trying to align themselves with this imagined master clock. Of course, Newton knew that real clocks are messy. Pendulums slow down, springs weaken, friction eats into motion. But these imperfections did not bother him. They were practical engineering details. In the mathematical heart of his theory, time remained perfectly regular. You could always imagine an ideal clock, a device that would tick in perfect agreement with absolute time if only you could build it. Real clocks were approximations of this ideal, and making them better was mostly a matter of craftsmanship. The success of Newtonian physics made it easy to forget that this was a choice, not a logical necessity. For motions at everyday speeds and in moderate gravitational fields, Newton's laws work beautifully. Planets trace predictable paths. Projectiles arc in tidy curves. Engineers design bridges and engines with confidence. In this regime, treating time as absolute is not just convenient. It is practically indistinguishable from the truth. You do not notice any discrepancy because the effects that would reveal it are tiny. But even within classical physics, small hints of trouble lurked. The laws that govern electricity and magnetism, written down by James Clerk Maxwell, looked slightly different under simple Newtonian ideas of space and time. The speed of light, in particular, seemed to be the same in all directions and for all observers, which did not fit well with the idea of absolute rest. Physicists tried to patch this with the idea of an invisible medium called the ether, through which light waves might ripple, yet experiments failed to detect any motion through this ether. The cracks whispered that something about the underlying stage of space and time was not quite right. At the human level, none of this was obvious. Trains did not seem to care about the speed of light. Industrial machines did not warp or twist as they moved. For almost all practical purposes, Newton's clockwork universe worked. You could live your entire life, build entire industries, and never notice that the deeper structure of time might be more flexible than you imagined. That is part of what made the coming shift so dramatic. By the end of the 19th century, physicists were staring at a strange mismatch. Their mechanical picture of the world, built on Newton's absolute time and space, was enormously successful. Yet their newest, most precise theories of light and electromagnetism did not sit comfortably on that stage. They fit better with a world where the speed of light has a special status, one that no motion can quite erase. Something had to give. In the next part, we will watch that give play out. A young patent clerk named Albert Einstein will take the constancy of the speed of light seriously and ask a radical question. What if time itself is not absolute? What if different observers, moving relative to one another, actually live in different slices of time? The comfortable image of a single cosmic clock will begin to dissolve, replaced by a world where moving clocks tick at different rates and simultaneity becomes a local, not a universal, idea. The clockwork universe will not vanish, but its gears will turn out to be embedded in a deeper, stranger structure than Newton ever imagined. By the late 1800s, physics looked almost complete. Newton's clockwork universe described the motion of planets and projectiles. Engineers built machines and bridges with his laws in mind. Time was treated as a single smooth parameter, the same everywhere, ticking along in the background. Yet right in the middle of this confident picture, a strange kind of light began to cause trouble. The very force that lets you see the world was whispering that space and time might not be what everyone thought they were. Electricity and magnetism had grown from scattered curiosities into a unified theory. Scientists like Faraday and Maxwell showed that electric and magnetic fields are not separate things. Change one and you create the other. Maxwell wrote down equations that tied these fields together. When he solved them, he found that they predict waves. Disturbances in the fields ripple outward through space at a fixed speed. When he calculated that speed, it matched the measured speed of light. Light, it seemed, was an electromagnetic wave racing through space. Here is the problem. Every wave they knew at the time needed some medium. Sound waves need air or something else to vibrate. Water waves need water. If light is a wave, what is waving? Space was thought to be empty. So physicists imagined an invisible substance filling all of space, a weightless, perfectly transparent medium that carried light. They called it the ether. You could not see it. You could not touch it. Yet it was meant to be the thing that defined absolute rest. If you moved through this ether, you should feel a kind of cosmic wind. Once that idea took hold, it suggested a simple way to test it. Earth orbits the Sun at tens of thousands of kilometers per hour. If the ether is there, our planet should be ploughing through it. Light moving in the direction of that motion should be slightly slower or faster relative to an observer than light moving sideways to it, just as a swimmer feels a difference when swimming upstream instead of across a river. The effect would be tiny, but with careful measurement it should be detectable. Albert Michelson and Edward Morley set out to detect it. They built an instrument called an interferometer on a heavy stone slab that floated on a pool of mercury, so it could rotate with minimal friction. The idea was elegant. Split a beam of light into two paths at right angles, send them down long arms, then recombine them. If Earth is moving through an ether wind, the beams should experience slightly different travel times. That difference should show up as a shift in the pattern of light and dark bands called fringes when the beams meet again. They rotated the device to sample different directions. They repeated the experiment at different times of day and different seasons of the year, when Earth's motion around the Sun points in different directions. If there were an ether, the pattern should slide back and forth as the orientation of the apparatus changed relative to the ether wind. Instead, again and again, the result refused to budge. The shift they expected did not appear. Within the limits of their equipment, the speed of light looked the same in all directions. This was not just one awkward data point. Others repeated and refined the experiment with even greater sensitivity. The null result remained. No flicker of an ether wind showed up. The universe behaved as if there were no preferred rest frame, no hidden medium marking out absolute stillness. For a physics community steeped in Newton's absolute space and time, this was deeply uncomfortable. The ether had been a way to keep that absolute stage while still letting light be a wave. Its failure left both ideas wobbling. Physicists tried to save the ether with clever patches. Lorentz and Fitzgerald suggested that objects might actually contract in the direction of motion through the ether, by just the right amount to hide the expected fringe shift. Mathematically, this kind of contraction could explain the null result, yet it felt strangely conspiratorial. The universe would be arranged so that whenever you tried to measure your motion through the ether, lengths and times would distort in just the right way to fool you. The ether would exist, but it would be impossible to detect in principle. At the same time, practical technology was tightening the grip of shared time on society. Telegraph wires and railways spread across continents. Time zones were introduced. Observatories sent out regular time signals. People were not only thinking of time as absolute, they were building infrastructure that depended on that assumption. You could set clocks in different cities to match and believe that they were all tracking the same cosmic now. The idea that two observers might honestly disagree about whether two distant events happened at the same time did not fit easily into that world. Yet Maxwell's theory of electromagnetism kept insisting that light has a special speed that does not care about the motion of its source. The more precisely physicists tested this, the more stubborn the result became. In one camp, some tried to restore comfort by imagining that there really was a special rest frame, defined by the ether, but it was forever hidden behind a wall of distortions. In another camp, a few began to wonder whether the problem was deeper, whether time and space themselves needed to be rethought. From our vantage point, it is easy to see the story with hindsight. We know that the next step will be to give up the idea of absolute time and absolute space, and to replace them with something more flexible. But for the scientists living through it, that step was anything but obvious. They had a set of theories that worked extremely well in almost every situation, and a few troubling corners where things did not quite add up. Was that a sign of a small patch needed, or a sign that the foundations were crooked? In the next part, a young Albert Einstein will make a radical choice. He will take the constancy of the speed of light as non-negotiable, and ask what must give way instead. The answer will tear down the idea of universal time, and replace it with a world where moving clocks tick at different rates. Rulers shrink along their direction of motion, and simultaneity becomes relative. The cracks opened by the ether and the speed of light will widen into a new geometry for reality, where space and time fuse into spacetime and your path through it shapes your experience of duration. When Einstein entered this story, he did not look like someone who was about to change the meaning of time. He was a young man working in a patent office, reviewing designs for clocks and electrical devices. During the day, he read about gears, springs, and synchronizing signals. At night, he thought about light, trains, and lightning. The world around him still clung to the idea of a single universal time. The ether had failed its tests, but many physicists hoped that some invisible background would still rescue absolute space and absolute time. Einstein did something different. He let them go. He started from two simple principles. First, the laws of physics should look the same for all observers who move at constant speeds relative to one another. That means there is no preferred state of absolute rest. Second, the speed of light in empty space is the same for all such observers, no matter how they are moving or how the source of light is moving. These statements sound innocent, almost modest. Together, they collide with our everyday ideas of time in a dramatic way. You can feel the conflict by trying to hold on to your old intuitions. If you throw a ball forward on a train, someone standing on the platform will say the ball's speed is the speed you threw it, plus the speed of the train. That matches experience. If you try to treat light the same way, you would expect a beam sent from the front of a fast train to be faster for someone on the ground than for someone inside. But the experiments inspired by Maxwell's equations insisted that this is not true. Both observers measure the same speed of light. Something has to give, and Einstein decided that the thing that gives is our old sense of time and space. To see how, picture a very simple clock. Imagine a beam of light bouncing between two mirrors, one above the other, inside a small glass box. Each bounce from the bottom mirror to the top and back again is one tick. For someone standing next to the box, at rest with respect to it, the light travels straight up and straight down. The distance between the mirrors stays the same. If we know that distance and we know the speed of light, we can work out how long each tick takes. Now put that light clock on a train that glides past you at a steady, high speed. From the point of view of someone on the train, nothing has changed. The light still goes straight up and straight down between the mirrors. The ticks are just as regular as before, but from your point of view on the platform, the picture is different. While the light travels upward, the whole clock is moving forward with the train. The light does not trace a straight vertical line for you. It traces a diagonal path, up and forward, then down and forward. Each tick covers a longer distance in space. Here is the key twist. Both you and the person on the train must agree on the speed of light. The universe has decided that this speed is fixed for everyone. If the light on your diagram is covering a longer path but cannot go any faster, then it must take more time between ticks. For you, watching from the platform, each tick of the moving light clock lasts longer than for the person riding with the clock. Their moving clock runs slow compared to your rest clock. This effect is called time dilation. A clock that moves relative to you ticks more slowly than a similar clock that rests beside you. The faster it moves, the stronger the effect. At everyday speeds, the difference is so tiny that you never notice it. At speeds close to the speed of light, it becomes dramatic. The shock is that this is not an optical illusion. It is not a trick of delayed signals. Each observer uses their own clocks, right next to them, to measure durations, and they find that moving clocks genuinely tick at a different rate. The strangeness deepens when you remember that the person on the train can just as honestly say that they are at rest and you are the one moving. From their point of view, your light clock on the platform is the one tracing a diagonal path, because in their frame the station slides backward as the train goes forward. By the same reasoning, they conclude that your clock runs slow compared to theirs. Both are right within their own frames. There is no single, absolute answer to the question whose time is really slowed. This leads directly to another blow to common sense. We normally assume that if two events happen at the same time, everyone will agree on that. Einstein showed that this is not true once light speed is fixed and finite. Imagine a long train again. A bolt of lightning strikes the front of the train, and another bolt strikes the back. An observer standing midway along the platform sees the two flashes of light arrive at the same moment. Because the strikes are equally far away, they conclude that the bolts hit at the same time. Now picture an observer who is halfway along the train moving with it. At the instant the bolts strike, they are alongside the platform observer, but then the train moves forward. Light from the front strike has to chase the moving midpoint on the train, while light from the back strike meets it. The person on the train sees the flash from the front later than the flash from the back. They conclude that the bolt at the back struck first. Both observers are using the same rules. Both are honest and careful, yet they disagree about which event happened first. Simultaneity has become relative. To keep these stories consistent, space must also bend to the new rules. Along the direction of motion, lengths contract when measured by someone for whom the object is moving. This length contraction, together with time dilation and the relativity of simultaneity, forms a coherent new geometry of the world. Instead of absolute space and absolute time, there is a four-dimensional fabric called spacetime, where different observers slice the fabric into space and time in different ways depending on their motion. One of the most famous illustrations of time dilation is the twin thought experiment. Imagine identical twins. One stays on Earth, the other boards a spacecraft that accelerates to a speed close to the speed of light, travels out for a while, then turns around and comes back. During the high-speed parts of the trip, the traveling twins' clocks, including their own heartbeat and aging process, run slower than the clocks on Earth as judged from Earth's frame. When the twins reunite, the one who traveled has experienced less time and is younger. This might sound like pure speculation, but nature runs its own versions of this experiment. Particles created high in Earth's atmosphere travel toward the ground at speeds close to light speed. In their own rest frame, they decay quickly, yet in our frame their internal clocks run slow, so we detect them much farther down than we would if time flowed the same for them as for us. Atomic clocks flown on airplanes and satellites tick at slightly different rates than identical clocks left on Earth, exactly as relativity predicts once you account for both speed and gravity. At first, these effects feel like an attack on reality itself. If different observers cannot agree on the duration between events, or the order in which distant events happen, what is really going on? Einstein's answer is that the real, observer-independent thing is the entire space-time structure, the web of events and the paths through it. Each observer carries their own time with them along their path, called a world line. What you call time is the distance you travel along that path, measured in a way that mixes what you think of as space and what you think of as time. In everyday life, where speeds are tiny compared to the speed of light, all of this collapses back to Newton's familiar picture. The differences between frames are so small that you can pretend there is a single universal clock without getting into trouble. But our technology and our experiments have pushed far beyond that cozy regime. We rely on moving satellites whose clocks must be corrected for time dilation. We accelerate particles to speeds where their lifetimes stretch dramatically. The universe keeps confirming that time is not a single flow shared by all, but a flexible quantity woven together with space. In the next part, gravity will enter the scene. Einstein will realize that even this new, flexible picture is incomplete. Massive objects do more than simply sit in space-time. They bend it. Clocks do more than disagree because of motion. They also disagree because of where they sit in a gravitational field. We will follow falling elevators, orbiting clocks, and the edge of black holes to see how far time can be warped, and what happens when the very geometry of space-time becomes the storyteller of duration. Special relativity already told us that time is not universal. It stretches and shrinks depending on how you move. Einstein then asked a deeper question. What about gravity? For centuries, gravity had been treated as a force that pulls on masses across empty space. Newton could write down a simple formula that worked incredibly well. Yet something about this action at a distance bothered Einstein. He wondered if gravity might not be a force in the usual sense at all, but a sign that space-time itself was bent. That question would change our understanding of time more radically than ever. His way in was deceptively simple. Imagine you're in a small room with no windows. You feel a steady force pulling you down toward the floor. You drop a ball, and it accelerates downward. A beam of light entering through a hole in the wall follows a curved path before hitting the opposite side. Are you in a room sitting on the surface of a planet feeling the pull of gravity? Or are you in a rocket drifting far from any mass, with engines pushing you upward so that the floor presses against your feet? Inside the room, there is no experiment you can do that clearly tells the difference. Einstein elevated this to a principle. Locally, being in a gravitational field and being in an accelerating frame can feel the same. This equivalence between gravity and acceleration became the seed for a new picture. If acceleration can mimic gravity, and acceleration changes how time flows in special relativity, then gravity should also change the rate of time. Clocks deep in a gravitational field should tick at a different rate than clocks higher up, just as moving clocks tick differently from resting ones. Time itself must be woven into whatever gravity really is. From this insight grew general relativity. In this theory, mass and energy tell spacetime how to curve, and curved spacetime tells matter and light how to move. Planets orbit not because an invisible force pulls them in, but because they follow straightest possible paths in a warped geometry. You can picture a heavy ball placed on a stretched sheet, creating a dip with smaller balls rolling around that dip. The sheet is a crude analogy for spacetime. Where there is more mass, the sheet dips more deeply. The important twist is that time is part of that sheet. Gravity bends time as well as space. One of the cleanest predictions is gravitational time dilation. Imagine two identical clocks, one at the top of a tower and one down on the ground. The clock closer to the massive Earth sits deeper in the gravitational field. According to general relativity, time there should run a little slower. The clock on the tower should tick slightly faster. At first, this sounds absurd. How could height change the rate of time? Yet delicate experiments with atomic clocks have shown exactly this effect. Move a good clock up a mountain and it really does gain time compared to its twin at sea level. Light feels this warping too. A beam climbing out of a gravitational well loses energy. Since its speed stays the same, this loss shows up as a stretching of its wavelength, a shift toward red. This is called gravitational redshift. Astronomers see it near massive stars and compact objects. In laboratories, physicists have bounced light up and down tall towers and measured tiny frequency shifts that match the predictions of general relativity. Once again, time is not just a neutral background. It slows near mass. It speeds up farther away. Every gravitational field shapes the tempo of the universe around it. Now push this idea to extremes. Suppose you gather enough mass into a small enough region that space-time bends so severely that even light cannot escape. This is a black hole. Outside a certain boundary called the event horizon, light rays can still climb out with effort. Cross that boundary and all paths lead inward, deeper toward the center. Time and space trade roles in strange ways. The horizon is not a physical surface. It is a point of no return, a place where the structure of space-time itself funnels everything inward. The most unsettling part is what happens to time near this horizon, seen from different viewpoints. Picture an astronaut falling feet first toward a black hole. From the astronaut's own perspective, their watch ticks normally, their heart beats. They see the horizon rushing up to meet them. Within a finite amount of proper time on their own clock, they cross the horizon and continue inward. Nothing special marks the crossing in their immediate surroundings if the black hole is large enough that tidal forces are gentle there. A distant observer watching from far away sees something completely different. They see the astronaut falling, but as the astronaut approaches the horizon, their signals climb out of an ever deeper gravitational well. Each wave of light is stretched more and more. The astronaut's image grows dimmer and redder. Their motions appear to slow. From the distant viewpoint, the astronaut never quite crosses the horizon. Instead, they seem to freeze and fade, taking an infinite amount of faraway time to reach that boundary. Time near the horizon is so warped that the outside world watches the fall as if it is endlessly stretched. This difference is not a glitch. It is built into the geometry of space-time around black holes. There is no single objective answer to the question, how long did it take the astronaut to fall in? For the astronaut, the journey has a definite duration on their own clock. For the distant observer, the approach to the horizon drags on without end. Both stories are correct within their own frames. Once again, we are forced to give up on the idea of a universal time that all observers must share. Gravity has shredded that idea even more severely than motion did. The warping of time near massive objects is not just a curiosity of black hole lore. It matters in technologies we use every day. The satellites that provide global positioning carry clocks that experience less gravity and move faster than clocks on Earth's surface. Special relativity says their motion slows their time. General relativity says their weaker gravity speeds it up. Engineers must account for both effects to keep the system accurate. If they ignored the general relativistic correction, the positioning system would wander off by kilometers. Our machines already live in a world where time is a flexible quantity shaped by space-time. General relativity also reshapes how we think about the history of the universe itself. If space-time can curve, then on the larger scales it can expand, contract, or oscillate. The same equations that describe falling apples and orbiting planets point back toward a hot, dense beginning. They allow for regions so curved that they form black holes, and for waves of curvature that ripple outward when massive objects collide. In every case, time is not just a parameter that runs in the background. It is part of the dynamic fabric that bends, stretches, and sometimes tears. We have now seen time stretched by speed and warped by gravity. We have watched clocks disagree on moving trains, on mountaintops, in orbit, and near the edge of black holes. The comfortable idea of a single cosmic tick has been replaced by a woven tapestry of local times, each attached to a path through space-time. In the next part, we will dive into the quantum world, where certainty cracks and probability rules. There, time takes on an even stranger role, hovering between a simple parameter and something that might emerge from a deeper, timeless reality. So far, time has looked like a flexible but still familiar parameter. It stretches with speed, warps with gravity, and depends on your path through space-time. Yet in all those stories, things still happen in a clear order. Causes lead to effects. Clocks tick along their world lines. The underlying laws take states of the universe and move them forward in time. When we shrink our view down to the quantum world, even that simple picture wobbles. Time is still there in the equations, but its role becomes strangely ghostly. Quantum mechanics began as a desperate attempt to explain experiments that refused to fit classical expectations. Light behaved like a particle in some experiments, and like a wave in others. Electrons did the same. The new theory that emerged described particles not as tiny billiard balls with well-defined positions and velocities, but as objects that sometimes behave like waves and sometimes like point-like hits. More precisely, it described them with mathematical waves that encode probabilities. Where the wave is large, a detection is likely. Where the wave is small, a detection is unlikely. One of the clearest windows into this weirdness is the double-slit experiment. Imagine a source of electrons, and in front of it a screen with two narrow openings. Beyond that, a detector screen records where each electron lands. If you send many electrons through, and do not try to watch which slit they pass, the pattern on the back screen is not just two bright bands. It is an interference pattern, a series of bright and dark stripes, exactly what you would expect from overlapping waves. Somehow each individual electron behaves as if it explores both paths and interferes with itself. Now change the setup. Add detectors near the slits that can tell you which opening each electron actually goes through. Run the experiment again. The interference pattern disappears. The electrons now behave like tiny pellets that choose one path or the other, merely setting up a way to gain which path information changes the outcome. The wave description and the particle description seem to trade places depending on what is measured. The moment of measurement becomes a kind of hinge between different realities. In the standard way of talking about quantum mechanics, the wave that describes a system spreads out and evolves smoothly in time according to a deterministic equation. Then, when a measurement is made, that wave abruptly collapses into a specific outcome. Before measurement, the particle is said to be in a superposition, meaning it has many possible properties at once, each with a certain weight. After measurement, one definite value is obtained. Time in this story does two different jobs. It smoothly carries the wave forward, and then it marks a special instant when possibilities snap into a single fact. Why should that instant be special? The theory itself does not say. Things get even more unsettling in delayed choice experiments. In one version, you let a particle enter a device where it could behave like a wave or a particle, but you decide only at the last moment which kind of measurement to perform. If you choose the wave-like measurement, you see an interference pattern, as if the particle took both paths. If you choose the particle-like measurement, you see outcomes as if it took only one path. The surprise is that your choice of measurement seems to reach backward and change what the particle must have been doing. It is not that you rewrite the past in a crude way. Rather, the theory resists any simple story in which the particle had a definite trajectory before you looked. Entanglement pushes this tension across space. Prepare two particles in a shared state so that their properties are linked. Send them far apart. When you measure one, you instantly know what result you will get if you measure the other, even if it is on the other side of a galaxy. Experiments confirm that these correlations cannot be explained by simple, hidden instructions carried from the past. They show up in ways that violate inequalities that any local classical model would obey. Time still flows forward. You never see information jump faster than light in a way that lets you send messages. Yet the pattern of outcomes has a global, timeless flavor, as if the pairs knew all along how they would match. In the background of all this, time in the equations is a smooth parameter. The wave describing the system evolves in time, much like a vibrating string. You can write down a state at one time and a rule that takes you to a state at a later time, yet that evolution does not look like a story in which a definite reality marches forward. It looks more like the reshaping of a cloud of possibilities. The only moments when you get sharp facts are the moments you call measurements, and the theory does not clearly say what counts as a measurement or why. Some physicists try to tame this by changing the story rather than the predictions. In one family of ideas, often associated with many worlds, the wave never really collapses. All outcomes happen in a larger branching structure. What you experience as the passage of time is your mind sliding along one branch of this structure, remembering only one chain of events. In another family of ideas, the collapse is real and involves some new physical process, perhaps linked to gravity or complexity. In yet another, there is no collapse and no branching, only a hidden layer of variables that restore definite trajectories. In every case, time is present, but its relationship to events is more like a pattern of consistency than a simple before and after. There is also a question about whether time is fundamental at all in the deepest theories that try to unite quantum mechanics with gravity. Some approaches treat spacetime as emergent, like temperature or pressure. Individual molecules do not have a temperature. A large collection of them does. In the same way, perhaps individual quantum degrees of freedom do not have a built-in time. Time might arise only when you look at many of them in the right coarse-grained way. In these pictures, the flow of time that you experience could be a kind of large-scale illusion, a summary of deeper, timeless dynamics. Hints of this idea appear in thought experiments that combine black holes, quantum fields, and information. One line of reasoning suggests that the fundamental description of a region of space with gravity might live on a lower dimensional boundary, somewhat like a hologram. The way that description rearranges information can mimic the passage of time in the higher dimensional bulk. Here, time looks less like an ingredient and more like the way certain patterns change when you zoom out. Even in more modest quantum systems, there is a twist known as the problem of time. In some formulations of quantum gravity, the equations that are supposed to tell you how the universe behaves do not contain a time parameter in the usual way at all. They describe relations between configurations rather than evolution from one to the next. To get something like a flowing time back out, you have to pick one part of the system and use it as a clock, then see how the rest changes relative to it. Time becomes relational, not absolute. It is whatever one part of the universe uses to track change in another part. From the perspective of daily life, this is dizzying. You wake up, your alarm goes off, you go to work, you age. Time feels like the most basic ingredient of your experience. Yet in the quantum description of the world, time can slip out of the fundamental slot and show up instead as a convenient parameter, or as a pattern that emerges when many things interact. The laws may be perfectly happy to describe a timeless web of correlations. The flow you feel may be something your brain constructs while surfing that web, so we are left with a double mystery. Quantum mechanics describes reality with astonishing success, yet leaves us with a blurred picture of what is real when nothing is being measured. Time appears in its equations, but the way it connects to definite events, causes and records is murky. In the next part, we will turn to a very different route into the nature of time, one grounded not in particles and waves but in disorder and probability. Entropy will enter the stage, and with it the arrow of time, the one-way direction from past to future that your coffee, your memories, and the entire visible universe seem to obey. Deep down, many of the laws we have talked about so far do not care which way time runs. If you filmed two particles bouncing off each other and then played the movie backwards, the motion would still obey Newton's laws or the quantum rules. The equations of electromagnetism work just as well when you swap past and future. Yet your life does not feel that way at all. You grow older, not younger. You remember yesterday, not tomorrow. Coffee cools down, houses crumble. There is a clear direction from past to future. That direction is what we call the arrow of time. One of the easiest ways to feel this arrow is in a kitchen. Crack an egg into a pan. The yolk and whites spill out and mix. Heat them, and you get a scrambled mess. You never worry that the egg might suddenly leap back together into a perfect shell on the counter. That would be so strange that you would question your sanity. The laws of mechanics do not strictly forbid it, but in practice it never happens. Something is pushing the world towards states that look more mixed, more spread out, more disordered. Physicists use the word entropy to talk about this tendency. At first, entropy was just a quantity in thermodynamics, a way to describe how heat and energy flow. Later, thanks to the work of people like Boltzmann, it took on a deeper meaning. Imagine you look at a system only in a blurry way. You see the big picture, not the positions of every atom. For example, you see that all the air in a room seems evenly spread out. There are many, many different microscopic arrangements of molecules that would all look like that to you. They all count as the same macrostate. Entropy is, roughly, a measure of how many microscopic arrangements correspond to that big picture state. Now imagine a different macrostate. All the air molecules huddled in one corner of the room, leaving the rest empty. That is a perfectly allowed arrangement, but compared to the evenly spread case, there are far fewer ways to arrange the molecules so that they all stay in that corner. The high entropy state, where the air fills the room, has an enormous number of microstates. The low entropy state, all in one corner, has far fewer. If the molecules move randomly and explore their possibilities, they will spend almost all of their time in states that look high entropy to you. That is the heart of the arrow of time. The microscopic laws let the system wander freely through its space of possible arrangements. If you started in a very special low entropy state, there are many more ways for it to become a mixed high entropy state than to stay special. So as time passes, the system is overwhelmingly likely to move toward higher entropy. You never see the egg unscramble or the perfume leap back into its bottle, because those would require a fantastically precise conspiracy of motions. They are not impossible, they are just unimaginably unlikely. Think of shuffling a deck of cards. You start with a new deck, in a neat order. That is a low entropy state. After a few good shuffles, the deck looks random. There are so many more random-looking orders than orderly ones that you will almost never, by accident, return to the original arrangement. The shuffling procedure does not know anything about order or disorder. It simply mixes. Yet the space of possibilities is lopsided. High entropy dominates. The direction from neat deck to messy deck is the easy direction. The reverse is like winning a lottery with odds that do not fit in your brain. This statistical view also explains why you remember the past but not the future. Records of events, whether they are footprints, photographs, fossils, or memories in your brain, are all physical structures. To create them, you have to increase entropy somewhere. Your brain lays down patterns of connections between neurons. Cameras rearrange charges on a sensor. Each act of recording leaves a trail of increased disorder in the environment. Those trails point backward to earlier states. You have no similar trails coming from future events. The direction in which information accumulates is the same direction in which entropy increases. There is a small catch. If the microscopic laws are mostly symmetric under time reversal, you could imagine a world where entropy increases toward what you call the past instead. Why does your universe show low entropy in the past and high entropy in the future, rather than the other way around? The answer seems to be that you were simply born into a world that started in a very low entropy state, and you experienced the growth away from that. The arrow of time is tied not so much to the laws themselves as to the boundary conditions, the starting conditions of the cosmos. This connection was already troubling in the time of Boltzmann. He knew that if you let a gas evolve from a special low-entropy state, it will almost certainly move toward equilibrium, where everything is evenly spread out and nothing interesting happens. But he also knew that if you pick a state at random from the set of all possible states, it will almost certainly already look like equilibrium. So why does our universe seem to be in the middle of an entropy climb rather than at the flat top of the hill? Why is there a hill to climb at all? In everyday situations, you can dodge this deep question. You can say that the low entropy state of your coffee, with heat carefully stored in the liquid and not the room, came from an even lower entropy state in the kettle, which came from an even lower entropy state in the power plant, and so on. You pass the buck backward. But if you keep pushing, eventually you reach cosmic scales. You have to ask why the early universe, shortly after the Big Bang, was so incredibly orderly compared to what it could have been. There is another layer to this story involving information. When you increase entropy, you're often losing track of detailed information about a system. The precise positions and velocities of particles become smeared into averages and probabilities. You can never get that fine-grained information back in practice. Heat death of the universe, a phrase that haunted 19th century thinkers, is the idea that if entropy keeps climbing, the cosmos will end in a state where there are no large-scale gradients left to drive interesting processes, no free energy to run complex structures, just a thin, lukewarm fog of matter and radiation drifting toward uniformity. At the same time, the arrow of time is what makes your life story possible. You age because cells accumulate damage and lose their original structure. Buildings decay because materials crack, corrode, and crumble. Stars burn their fuel and evolve. Every process that leaves a record, every memory, every scar, every fossil, leans on entropy increasing somewhere. The cost of history is disorder. The reason you can tell a story with a beginning, middle, and end is that the physical world has a direction in which new marks can be written, and old marks fade. Notice how different this is from the way relativity bent time. In special and general relativity, the equations themselves already allow different observers to slice spacetime differently, and to experience different rates of time. In the statistical view of entropy, the basic laws happily run both ways. The arrow arises when you ask what is typical and what is rare given some starting state. One kind of weirdness is built into the geometry of spacetime. The other is built into the counting of possibilities. Yet your day-to-day sense of time depends on both. So when you watch cream swirl into coffee or smoke drift away from a candle, you are witnessing a deep truth. The future is the direction in which entropy increases. The past is the direction in which it was lower. Your own mind tracks that direction by storing records and calling them memories. In the next part, we will zoom out to the entire universe and ask the troubling question that entropy leaves hanging. If high entropy states are so overwhelmingly likely, why did the universe begin in a state of such astonishing low entropy? Black holes, cosmic expansion, and the faint afterglow of the Big Bang will enter the story, and with them one of the biggest puzzles about time that physics has yet to solve. When you pour milk into coffee and watch the swirl, you're watching entropy climb in a tiny kitchen universe. Now stretch that idea to everything that exists. The visible universe is also running on an entropy gradient, drifting from an impossibly special past toward a more disordered future. The unsettling question is why there was such a dramatic hill to roll down in the first place. If high-entropy states are overwhelmingly more common than low-entropy ones, why did the universe begin in a state that looks so strangely ordered? The standard story of cosmic history begins in a hot, dense, early state. Not a point in ordinary space, but a phase where the universe was much smaller, filled with a nearly uniform plasma of particles and radiation. Temperatures were unimaginably high. Matter and light were tangled in a glowing fog. At first glance, that sounds like chaos, hot, dense, everything colliding with everything else. Yet from the point of view of gravity, that smooth, uniform soup is the opposite of chaos. It is an extremely low entropy arrangement. To see why, think back to the room full of air. When gas molecules are spread evenly, that is high entropy for the gas itself. But gravity wants to clump matter. It rewards lumps, clusters, and collapses. A universe where matter is spread out smoothly has enormous room to increase its gravitational entropy by forming structure. Stars, galaxies, and especially black holes are ways for gravity to rearrange matter into configurations that are far more numerous at the microscopic level. The young universe, smooth and nearly featureless, was balanced on the very top of a hill of gravitational possibilities. We have a photograph of that youth in the form of the cosmic microwave background. This faint glow of microwaves fills the sky, the cooled remnant of the time when the universe became transparent and light could finally travel freely. Satellites have mapped it in detail and found that it is astonishingly uniform in temperature, varying only by tiny fractions of a degree from place to place. Those small ripples are the seeds of later structure, but the overall picture is one of remarkable smoothness. That smoothness is a clue that the early universe had low gravitational entropy. As the universe expands, something dramatic happens. Tiny overdensities, places where matter is slightly more concentrated than average, begin to pull in their surroundings. Gravity amplifies small differences. Over billions of years, that leads to webs of galaxies, clusters, and vast empty voids. Stars ignite in the dense knots, shining by transforming nuclear fuel into radiation, and in the process increasing entropy. Clouds collapse, disks form, planets condense, and waste heat leaks away into the cold. The universe turns its low-entropy starting conditions into a growing menagerie of structure and disorder. Black holes sit at the extreme end of this process. When enough mass collapses into a small region, spacetime curves so strongly that an event horizon forms. From the outside, all the detailed information about the matter that fell in is hidden. Remarkably, calculations in general relativity and quantum field theory suggest that a black hole has an entropy proportional to the area of its horizon. In simple language, the number of possible internal microscopic configurations that would all look like the same black hole from the outside is staggeringly huge. A single large black hole can carry more entropy than all the ordinary matter around it. This turns black holes into powerful entropy engines. As massive stars die and collapse, as gas falls into galactic centers, as mergers build ever larger holes, the gravitational entropy of the universe soars. The smooth early plasma had none of these monsters. The late universe, speckled with black holes of many sizes, looks far more disordered in gravitational terms. So we land on a paradox. If high entropy configurations dominate, why did the universe begin in a state that was so smooth that it left most of its entropy potential unused? One line of thought associated with ideas like Penrose's Weyl curvature hypothesis points to the shape of spacetime itself. It suggests that the early universe had very low gravitational entropy because its geometry was special in a particular way, with little of the kind of curvature associated with clumping and black holes. Over time, as structure forms and holes appear, that part of the curvature budget fills up and entropy rises. This does not yet tell us why the initial geometry was so special. It shifts the question onto the deep boundary conditions of spacetime. Another influential idea is cosmic inflation. According to inflation, a tiny patch of space in a special state underwent a brief period of extremely rapid expansion in the early universe. That expansion smoothed out irregularities and stretched quantum fluctuations into the seeds of galaxies. Inflation explains several puzzles at once, including why regions of the cosmic microwave background that are far apart today have nearly the same temperature. It also makes the universe look flat and similar in every direction. But inflation does not fully solve the low entropy problem. It assumes an initial state that allows inflation to start, and that state itself may already be very special. Some physicists push the question into an even larger landscape. They imagine a multiverse, a vast ensemble of regions with different laws or different initial conditions. In most of those regions, conditions may not allow complex structures or observers at all. We find ourselves in a low-entropy bubble, simply because only such bubbles give rise to beings who can ask questions about entropy. This is a kind of anthropic reasoning. It does not give a precise mechanism so much as an explanation for why the universe we see is so unlikely when judged against all possible ensembles. It also leaves many people unsatisfied, because it leans heavily on unobservable possibilities. Black holes add another twist to the story through the problem of information. When matter falls into a black hole, its detailed state seems to disappear behind the horizon. If the black hole later evaporates through a slow leak of radiation, as Hawking's calculations suggest, what happens to that information? If it is truly lost, the underlying laws might not be reversible even at the microscopic level, which would give entropy an even more fundamental arrow. If the information is somehow encoded in the radiation, or in a deeper description of spacetime, then entropy remains a statistical story, but one that plays out in a very unfamiliar arena. This debate has driven much of modern thinking about quantum gravity. All of this circles back to your everyday arrow of time in a surprising way. The fact that you live in a universe where stars formed, where heavy elements were cooked in their cores, where planets cooled and chemistry blossomed, depends on that early low-entropy state. Without it, there would be no long fall from order into disorder, no free energy to power biology, no gentle gradients to fuel thought. Every memory you have is a tiny echo of the cosmic choice that set the initial conditions. Every cup of coffee cooling on a table is a miniature reenactment of the universal drift toward higher entropy. We do not yet know why the universe started in such a special way. We have candidate stories, mathematical frameworks, and suggestive hints from cosmology and black hole physics. We can calculate how entropy evolves once the game begins. We can describe how structure forms and dissolves. But the deepest why remains open. In the next part, we will step away from equations and look at how these ideas about time shape our picture of reality itself. Block universes, flowing presents, and questions about free will take the stage as we try to reconcile a cosmos where past and future may be equally real with a life lived in a single, moving now. By now, our picture of time is already strange. It stretches with speed, warps with gravity, and carries an arrow set by entropy. Relativity adds one more unsettling ingredient. It quietly suggests that past, present, and future might all be equally real. The flow you feel could be less like a river in the world and more like a spotlight moving across a fixed landscape. That thought is both beautiful and deeply uncomfortable, especially when you ask where your choices fit into it. Relativity does this in a sneaky way. Once you accept that simultaneity is relative, you lose the idea of a single universal now that slices through the universe. Observers in different states of motion carve up spacetime into past, present, and future in different ways. Two events that you call simultaneous might be ordered differently by someone rushing past you, yet the underlying spacetime does not care. It is a four-dimensional web of events and world lines, all laid out together. When you draw it, you do not really see a flowing moment, you see a block. This leads to what is often called the block universe picture. In that view, spacetime is like a four-dimensional sculpture. Every event that ever happens is a point in that sculpture. The birth of a star, the fall of a raindrop, your first day at school, your last breath, all of them are already there as parts of the whole. You, as a conscious being, trace out a path through this structure. What you call now is just the place where your awareness currently sits along your path. If that is the case, then the future is not something that gets created moment by moment. It is already there, waiting for you further along your world line. The past is not something that vanishes. It remains as another region of the structure. The difference between past and future is not about existence. It is about how they relate to you and to the entropy gradient that underlies memory and records. That is a hard idea to swallow because it feels like it flattens life into a frozen tableau. Some people find this block picture liberating. It suggests a kind of cosmic permanence. Nothing that happens is ever truly erased. Your entire life has a place in the structure of reality. Others find it suffocating. If the future is already there, in what sense can you say you could have done otherwise? Are you just a character reading lines that have already been written? The tension between these reactions pulls us straight into the old debate about free will. One response is a version of determinism. In a strictly Newtonian world with absolute time, determinism meant that the present state plus the laws fix the future and the past. In a block spacetime, determinism can mean that the geometry and the fields on it satisfy certain equations that admit only one consistent whole. You do not push the universe forward in time. The universe simply is. Your choices are part of that is. They are not outside forces beating against the structure. They are patterns within it. There is a softer view called compatibilism. It starts by asking what you really want when you say you want free will. Usually you mean that your actions flow from your own reasons, values and character, not from someone holding your hand on a puppet string. Compatibilism says that can be true even in a block universe. In the block, there is a region where you weigh options, imagine futures, feel conflicted and finally decide. That entire pattern is part of the structure. You are free in the sense that your acts come from who you are, even if the whole pattern is fixed by deeper laws. Other philosophers and physicists resist the block model altogether. Presentist views insist that only the present is truly real, and the past and future are in some sense unreal or less real. Growing block views treat the past and the present as real, with the future still open and undefined. In those pictures, space-time is not a finished sculpture, but a structure under construction, with new events becoming real as time passes. The challenge is to make these ideas fit comfortably with relativity, where different observers disagree on which events count as the present. There is also the possibility that both sides are missing something. Perhaps space-time is not the final word. If time is emergent from deeper quantum or information-theoretic structures, then the block that relativity draws might itself be an approximation. At that deeper level, the difference between past and future, or even the distinction between what exists and what does not yet exist, could look very different. Your sense of moving through time could be like your sense of color, a real feature of experience rooted in brain processes, but not a simple mirror of the outside world. Entropy and the arrow of time add another layer to this puzzle. In the block picture, the entire history of entropy increase is part of the structure. There is a slice where the universe is smooth and low entropy, slices where stars form and burn, slices where black holes dominate, and perhaps slices far in the future where almost all structure has faded. You live in a region where entropy is rising and where records accumulate toward what you call the past. Your sense of the future being open may be tied to the fact that you have no records of it, and to the way your brain constantly simulates multiple possible paths forward. Neuroscience hints at how this could feel from the inside. Your brain is not a passive camera. It is a prediction engine. It takes past experience and current input and constantly generates likely next moments. It then updates those predictions as new information arrives. The feeling of a moving present might be the feeling of that predictive machinery in action, always leaning forward, always testing what comes next against what it expected. In a block universe, that predictive activity is part of the sculpture. In a more dynamic universe, it lives on the leading edge of what is becoming real. Either way, your inner time is more about expectation and memory than about directly touching a flowing river. This does not make time meaningless. It makes it layered. At one level, there is the geometric structure of space-time, with different observers carving it into time and space in different ways. At another level, there is the thermodynamic arrow, which tells you which direction in that structure carries increasing entropy and accumulating records. At yet another level, there is the psychological arrow, the way your mind links memories into a narrative and projects possibilities forward. These arrows usually line up. You remember lower entropy states as the past, higher entropy states as the future, and your consciousness marches along in that direction. When those arrows pull apart, things feel uncanny. Conditions like certain neurological disorders can distort a person's sense of the sequence and duration of events, even though the external world keeps its usual order. In thought experiments, science fiction plays with worlds where memory runs backward, or where people glimpse fixed future scenes. These stories disturb us because they tangle the three arrows. They remind us that our intuitive sense of a uniquely flowing present sits on top of layers of physics and biology that do not share that simplicity. In the end, the block universe debate is not just about geometry. It is about what you count as real. The equations of relativity are happy to describe a four-dimensional structure without privileging a moving now. Entropy and quantum theory are happy to talk about patterns and correlations without naming a single moment as special. Your experience, however, insists that there is a now, that you stand on a narrow ledge between a fixed past and an open future. Whether that ledge is an illusion, a coarse-grained feature, or a fundamental slice of reality is still an open question. In the next part, we will loosen the reins even more and ask what happens if we try to push against time directly. We will examine time machines, wormholes, and paradoxes, and see how the laws of physics both invite and resist the idea of travelling to different points in the temporal landscape. Along the way, we will test how much abuse causality can take before the universe itself seems to push back. By this point, time already feels loose. It stretches for fast-moving twins, slows near black holes, and bends into strange shapes in space-time diagrams. So it is tempting to take the next step and ask the question that stories have loved for more than a century. Can you actually travel through time? Not just experience time differently at high speed or in strong gravity, but deliberately jump from one era to another. Physics gives an answer that is both delightful and frustrating. Parts of time travel are absolutely real. Other parts live in a fog where the universe itself seems to resist you. Start with the easy win. Time travel to the future is not science fiction. Special relativity already told us that moving clocks run slow. General relativity added that clocks deeper in a gravitational field also run slow. Put those together and you have a simple recipe. If you want to travel into someone else's future, you go fast, or you dive deep into gravity, or both. When you return to the place you left, less time will have passed for you than for the people who stayed behind. You have effectively jumped forward along their timeline. In practice, we already do small versions of this. Astronauts on the International Space Station orbit Earth at high speed and at a higher altitude than you. Both effects slightly change their rate of time. When they come back, their bodies and their clocks have experienced a tiny bit less time than those on the ground. The difference is measured in fractions of a second, but it is real. If we had the engineering power to build ships that cruised close to the speed of light, or to visit stable orbits near black holes, we could create much more dramatic leaps. You could leave on a journey that lasts a few years for you, and return to find that centuries have passed on Earth. Time travel to the past is where trouble begins. The simplest way to imagine it in relativity is through the idea of closed time-like curves. In plain language, that means a path through space-time that always moves forward in local time for the traveller, yet loops around so that it returns to an earlier point in the global history. Follow such a path and you could, in principle, shake your own hand from yesterday. General relativity contains solutions that admit these loops. Rotating universes, spinning cylinders that extend forever, and certain wormholes all seem to allow time-like paths that circle back. Wormholes are especially seductive. You can picture them as tunnels that connect two distant regions of space-time. In the simplest drawings, they look like a throat joining two mouths on a folded sheet. Enter one mouth, and you can emerge far away almost instantly. The equations of general relativity do allow such structures, at least as mathematical possibilities. They raise a thrilling prospect. If you can move one mouth of a wormhole relative to the other, speeding it up or dropping it into a deeper gravitational well, then their clocks will disagree. Step into the younger mouth and exit the older one, and from the outside it looks like you have travelled into the past. There are catches everywhere. The first is that maintaining a wormhole throat in a stable, traversable form seems to require exotic forms of matter that have negative energy density in some sense. Ordinary matter and radiation tend to make gravity pull inward and close the throat. To keep it open, you need something that acts like anti-gravity. Certain quantum effects can produce negative energy densities over tiny regions and times, but stretching that to a human-sized wormhole that stays open long enough for a traveller is far beyond anything we know how to build. It may be fundamentally forbidden. Even if you grant that the geometry could exist, time loops immediately run into paradoxes. The classic one is the grandfather paradox, where a traveller goes back and prevents their own ancestors from meeting. If they succeed, they were never born. and therefore could not have gone back in the first place. Another version involves messages sent into the past that prevent themselves from being sent. These stories offend our basic sense of cause and effect. They suggest a world where events erase the conditions that allowed them to happen. One proposed escape is the idea of consistency, the Novikov self-consistency principle, named after a physicist who explored these ideas, suggests that the universe only allows time loops where all events fit together without contradiction. You're free to travel around a closed time-like curve, but whatever you do on that loop must be compatible with the history that already exists. Attempts to create paradoxes simply fail in some way. The gun jams, the letter gets lost. You become, without realizing it, part of the very chain of causes that led to your departure. In this view, time travel does not create new histories. It reveals that what looked like a simple line was already a loop. Another escape leans on the many worlds flavor of quantum theory. In that picture, each time you perform a measurement or make a choice, reality branches into different consistent outcomes. A time traveler who arrives in the past may land not in their own history, but in a closely related branch. They can modify events there without altering the timeline that produced them. Paradoxes vanish because there is no single unique history to damage. You cannot erase your own origin. You can only create a new branch where things unfold differently. This is elegant on paper, but it pushes the idea of reality into a dizzying swarm of parallel histories. Stephen Hawking took a different approach. He suspected that nature itself might protect causality. He playfully called this chronology protection. The basic idea is that whenever a configuration of matter and spacetime begins to form that would allow closed time-like curves, quantum effects flare up in a way that destabilizes it. Energy densities near the would-be time machine blow up, the wormhole collapses, the spinning geometry pinches off, the universe censors itself before genuine paradoxes become possible. It is as if the laws of physics carry a built-in rule that history cannot be twisted into knots. We do not yet have a complete theory of quantum gravity, so these arguments are not final. Calculations in simple models suggest that quantum fields near the edge of a time machine behave badly, generating large stresses that feed back on the geometry. Whether this always happens, and whether it always happens in just the right way to seal off closed time-like curves, is still an open question. Many researchers suspect that any would-be time machine that tries to connect macroscopic regions in a causality-violating way will either be unstable or require unphysical ingredients. From a practical standpoint, the universe has already given a kind of answer. We see no sign of tourists from the future, no reliable messages sent backward, no natural systems that cycle through paradoxical histories. Our best working theories allow the serious bending of time to the future through speed and gravity. They entertain the mathematical possibility of loops in space-time, but they also hint that building or surviving such loops might be impossible. The equations welcome strange geometries. The quantum fields that live on those geometries seem to revolt. So the dream of stepping into a machine, dialing a date, and walking out into your own past remains in the realm of stories. That does not make the question meaningless. The fact that our laws of physics even brush against the possibility of time loops tells us something profound. Time is not as rigid as our instincts suggest, yet the apparent hostility of the universe to paradox also tells us something. Causality, the rule that effects follow causes in a consistent way, may be one of the deepest constraints on what is possible. In the final part, we will step back from wormholes and paradoxes and return to the scale of human lives. We will gather together everything we've seen, from subjective time in the brain to atomic clocks, from relativity to entropy, and ask what all of this means for how you live in the time you have. The physics of time may be strange, unfinished, and in some places still mysterious, but your hours and days are very real. How you understand them can quietly reshape how you move through your own small slice of the universe. We have walked time from the inside of your brain to the edges of black holes. We have watched it bend for fast-moving twins, slow near massive stars, smear into probabilities in quantum experiments, and pick up a direction from entropy. It is tempting to treat all of that as something far away, a set of curiosities that belong to laboratories and telescopes. Yet every one of those ideas quietly reaches into the most ordinary parts of your life. How you remember, how you plan, how you worry, and how you feel. Your days shrinking or stretching are all entangled with what time really is, and what it might not be. Start with the most intimate piece. Your sense of time is not a direct reading from a cosmic clock. It is a construction built from attention, emotion, and memory. When you're absorbed, hours vanish. When you're anxious, minutes swell. That means your experience of life is not only about how much time you have, but about how you shape it. 10 minutes of genuine presence with a friend or a book can feel fuller than an hour of distracted scrolling. Learning that your inner clock is flexible can be a kind of superpower. You can deliberately choose activities that drop you into flow when you want time to feel rich and quiet, mindful pauses when you want to stretch a moment instead of letting it blur. At the same time, accurate external clocks now govern much of the world you move through. Work schedules, deadlines, flights, financial markets, global calls, all rest on networks of atomic clocks and relativistic corrections that you never see. There is a strange contrast here. Your phone may be synced to a standard time defined by cesium atoms and orbiting satellites, accurate to fractions of a second across continents. Inside your head, time is fuzzy, warped by mood and context. Realizing that helps explain a lot of daily friction. The calendar and the clock are not wrong. Your brain simply plays by different rules. You can use that insight to be kinder to yourself. When a hard week feels endless, or a joyful day feels painfully short, it is not because time itself is punishing you. It is because your brain is stitching the story in a particular way. You cannot change the number of seconds in an hour, but you can change how densely you experience them. You can notice how novelty slows perceived time and routine speeds it up. You can choose to occasionally break patterns, take a new route, learn a new skill, or step out under a different sky, not only for the activity itself, but for the way it marks your inner timeline. Relativity adds another layer of perspective. You will probably never ride a rocket at 99% of the speed of light, but even the idea that time is not the same everywhere can shift how you see your place in the world. There is no single universal now. The person on the other side of the planet, the astronaut in orbit, and you reading this all inhabit slightly different slices of space-time. The universe does not elevate any one of those moments above the others. In a quiet way that levels things. Your now is not the center of time. It is one of countless local times woven into a vast structure. That can make personal crises feel both smaller and more poignant. Smaller because they are tiny ripples in a huge tapestry. More poignant because they are your ripples, the only ones you will ever directly feel. The block universe picture presses even harder on questions of meaning. If past and future are equally real in the geometry of space-time, then your life is a completed curve, every choice and event already part of the whole. It is easy to hear that and imagine that nothing matters, that you're trapped in a fixed script. But there is another way to read it. The fact that your life has a place in that structure does not make it less real. It makes it permanent. Every kindness, every shared laugh, every moment of courage or honesty exists forever as part of the shape of the universe. From inside the curve, you do not see that whole. You feel only the uncertainties at the leading edge, the fact that you do not know what you will decide tomorrow or how long you have. That ignorance is real. Even in a deterministic or block picture, you do not have access to the full script. You discover it as you go. The physics does not erase the importance of your choices. It simply says that whatever those choices are, they fit into the structure in a consistent way. Meaning is not handed down by time. It is written by what you do with the segment you can touch. Entropy and the arrow of time sharpen this further. You live in a universe that is moving from low entropy to higher entropy. That gives you a direction. It also gives you limits. There is only so much energy available to build complex structures and keep them running. Stars burn out. Bodies age. Memories fade. The same laws that let galaxies form and brains think also guarantee that both are temporary. This is stark, but it is also grounding. The scarcity of ordered moments is exactly what makes them precious. Knowing that entropy will eventually erase every detailed pattern can lead in two directions. One is despair. If everything ends in a thin blur of cold radiation, why bother? The other is a kind of fierce appreciation. The universe spent billions of years turning a smooth, hot plasma into stars, planets, oceans, and cells. It arranged particles into nervous systems capable of feeling and reflecting. For a brief time, in a tiny corner, you get to be one of those systems. You get to notice sunsets, taste food, listen to music, love people, and ask what time is. The fact that this arrangement is unlikely and temporary does not make it meaningless. It makes it a rare configuration worth inhabiting fully. Quantum mechanics pulls yet another thread through your life. At the deepest level we know, reality is described by probabilities and correlations, not by a simple list of definite facts marching forward. In that world, time is as much about patterns linking events as it is about a flowing river. You're not outside those patterns. Your brain is a quantum system embedded in a warm, messy environment, constantly decohering into definite outcomes. Your sense of a single history, one path through the space of possibilities, is part of that process. It suggests that uncertainty and branching futures are not just philosophical ideas. They are built into how the world explores its own options. When you stand at a crossroads in your life, it can feel as if you are looking down multiple timelines. In a technical sense, physics often treats the future as a set of weighted possibilities. In a personal sense, you do the same when you imagine outcomes and choose among them. Your decision changes which branch of that possibility tree you experience. Whether or not you believe in many worlds, the fact remains that you will only live one of those branches. Bringing awareness to that fact can make you more careful with important choices and more forgiving of yourself when you realize that no path is free of loss. There is also comfort in the unfinished nature of our understanding. After all of this, physics still does not have a complete unified picture of time. We do not know exactly how to merge quantum mechanics and general relativity. We do not know why the universe began in such a low entropy state. We do not know whether time is truly fundamental or a higher level pattern. The experts who write our best equations disagree on whether the flow you feel is an illusion or a key to something deeper. In other words, everyone is still guessing, just with better tools. For you, that uncertainty is an invitation rather than a threat. It means that curiosity is not a phase you grow out of. It is a natural response to living in a universe that has not finished explaining itself. You're allowed to marvel at both the accuracy of our clocks and the looseness of our theories. You're allowed to sit under a night sky, think about spacetime and entropy, and still feel startled by how quickly a year can pass. Science can deepen that sense of wonder rather than flatten it. So where does all of this leave you right now in your own small fragment of the timeline? It leaves you with a few simple, difficult truths. Your experience of time is flexible. Your supply of time is finite. The universe is stranger and less settled than it looks. You cannot slow the external ticking of the seconds, and you cannot step outside the flow of entropy. What you can do is pay attention to how you fill those seconds, how you structure your days, how you balance plans for the future with the reality of the present. In the end, time is both less and more than the river you grew up imagining. Less, because there is no single universal flow carrying everyone together from a clear past into an undefined future. More, because it is a tapestry woven from geometry, probability, information, and perception, all layered together. You are one bright, brief thread in that tapestry. You cannot see the whole pattern. You do not need to. It is enough to know that you are part of something vast, mysterious, and still unfinished, and to live your hours in a way that you would be glad to see preserved forever in the deep structure of time.